Hi everyone, let's get started. Welcome to the Data Science Seminar. It is our pleasure today to host Dr. Nathan TeBlunthuis, a postdoctoral research fellow in the Information School at the University of Michigan. He has previously at the Department of Communication Studies at Northwestern University and completed his PhD in communication at the University of Washington. Nathan is a computational social scientist who studies how collective action is organized in projects like Wikipedia, online communities like Reddit, and social movements. An important part of his work is to improve the measurement of meaningful communication behaviors from unstructured data, such as text and multimedia. The topic of Nathan's talk today is misclassification in automatic content analysis causes bias in regression. We know that, right? The question is, can we fix it? And Nathan says we can, and I'm looking forward to seeing how. Thank you.
All right. Thanks, Nicoletta. So I'm just going to dive right in, but first I'm going to say thank you to my collaborators on this work, Valerie Hayes and Changhan Chan. As Nicoletta said, I'm a computational social scientist. I don't need to review this slide because she already introduced me. But I'm going to talk today about this paper. It's currently still under review, Communication Methods and Measures, which is top methodological journal in my field. And so if you're interested, you can also find the paper and read it. So we're talking about automated content analysis. This is when it's a kind of study design, which is very popular in many fields, particularly in social science, where you use a supervised machine learning classifier to measure variables in text or other human interpretable high-dimensional data, like text, images, video. And so you build this classifier and then use it to automatically label your data, but there's a problem, which is that all of these machine learning classifiers, they're never perfect. There's always some errors. And these errors cause bias when you input the automatic classifications into a downstream statistical analysis. So suppose you want to measure toxicity in social media. You collect a data set of posts, you submit them to something like a perspective API or another classifier that makes predictions, and then you want to test the hypothesis about which types of messages are more toxic than others. That's the downstream analysis, and the fact that that classifier makes errors means that the estimate you're going to get back out is not going to be the same as if that classifier was always correct. But this is something that's not acknowledged as much as it should be in the literature. The current best practice in my field is transparency about this. So you train your classifier and you report how accurate it is in terms of precision, recall, or F1 scores. But I argue that we can do better. We have statistical methodology where we can use the validation data that we already have, that we were using to compute precision and recall, that we can use that same validation data to correct the misclassification bias. Okay. So that's basically the summary of the talk and the main points. I'm going to get into a lot more detail. But now I'm going to take a step back and ask, why are we using automated content analysis in the first place, right? If it has this problem with bias, why don't you just code a high-quality sample of data directly? Why bother using machine learning in this kind of study design at all? There's this little bar on the top. I'm just going to get rid of that. Okay. The first reason is that you can get a lot more statistical power if you have a large data set than if you have a small one. And often the kinds of phenomena or mechanisms that we're interested in testing, especially in large or in naturalistic settings, on social media, for example, they actually have pretty small effect sizes. So it's not like a small scale experiment where you're going to do a dramatic intervention and then be able to measure that with a small sample. Often the kinds of dynamics we care about are subtle, and you need a lot of data in order to be able to detect them. So we want to be able to gain statistical power, and that's one reason you want automatic classification. The second thing, and maybe a little more ambitious, is that we want to be able to build sort of generalizable measurement devices that we can use in a broad range of studies. So by reusing one model in many studies, we can better use resources in research, and we can also systematize how we measure things. Okay, but what's wrong with this is that we want to estimate like a model, like a regression model, y as a function of x and z, but we don't actually get to observe x, at least not outside of our validation data, which is a small sample. But in our large sample, we don't get to observe x. Instead, we are going to use w to stand in for it, where w is equal to x if our automatic classifier is correct, but it's the opposite of x if the classifier is wrong. So I'm setting this up in terms of a binary classification task, but we might, and there's a reason for that, and we can talk more about it later, but for now let's just stick with assuming that these are binary classifications. But the problem is that in general, the estimate for beta w in our model is going to be different than our estimate for beta x. Does that make sense? Okay. So now I'm going to show this in a real data example using the Perspective API. I already mentioned it. And part of the Perspective API's training data set is the civil comments data set. This is a data set of almost 500,000 comments that were annotated by humans for a number of variables, including this so-called toxicity measure, as well as identity disclosure, whether someone's disclosing whether they're, in this case, whether they disclose any element of their race or ethnicity. And then I'm also going to use a variable on likes. So how many times was this comment liked? And these are kind of similar to Facebook comments, although they're actually a different system that's a little bit older. But this is part of the training data set. And so this Jigsaw Perspective API, which is a widely used machine learning classifier that's hosted by Google, on this data set has an F1 score of basically almost 0.8, which is pretty good. This is above the normal bar for publishing a study that uses an automatic classifier to measure a concept in my field. But I'm going to show how in this toy example, logistic regression models with toxicity predicted or annotated will get different answers. So on the top above, we have a logistic regression where the outcome is whether someone discloses an element of their race or ethnicity. And the top row shows the estimates from the model where we use automatic classifications, and the bottom row shows the estimates we got using the manual annotations only, right? And we can see that for the direct effect of likes on disclosure, we find no detectable relationship using the classifications, but we find this small detectable relationship using the annotations. And this is to show that this can be a problem when you have automatic classifications in an independent variable that you're using to predict an outcome. And then below, we show that it also applies when you are automatically classifying the outcome of a logistic regression. So the automatic classifications falsely would have you say that there's a negative relationship between likes and toxicity, but using the manual annotations, you wouldn't be able to detect that. And this is with the same sample size. So this just goes to show you how this problem can be real. And we can also point out how, like these are pretty small effect sizes, and there's this interaction term in this model, and these things are done partly in order to construct a kind of scenario where this problem is most likely to happen, right? Where you have small effect sizes, and or you have like a complicated multi-variate regression model. Now, anyway, so that's sort of real-lit example. I'm just going to sort of check if that makes sense. Okay, so the point is that transparency about this classification is not enough. The fact that this model has a high F1 score does not protect us. It's not a guarantee that inferences that we make using its predictions are accurate. Okay, so now I'm going to show how, despite this fact, this is not something that much social science literature that uses automatic classifications talks about or attempts to address. So as part of our paper, we did a systematic literature review. We found 48 studies, each one represented by one of these little paper emojis. And each of these were using some type of automatic classifier. And 9 mentioned that the classifier makes errors and that those errors could threaten the validity of the study. But only 1 actually attempted to use any statistical method that would actually address the problem, or only 1 adjusted their statistical procedures in order to account for this threat. So the point is this is a largely ignored threat, but we might ask if we can fix it. And so now I'm just going to quickly demo an R package that we've built that provides procedure for fixing it. We call it GLM Fixit, and the package is called Misclassification Models. It's not in CRAN yet. Maybe someday it will be, but it's on GitHub. And what this package does is it creates this new, not really new, but like it uses this double pipe operator, right? So if you see that so race disclosed is a model, it's a function of toxicity coded, and then this double pipe operator, that means that we're going to use the toxicity predictions as our stand-in for the toxicity coded. The coded is like the true value, the predictions are the predictions, right? And then we pass both the prospective data and the validation data into this model, and then that way it will have both. It basically have like part of the data that you have every row observed, and then part of the data where you only have the validation data. And then the other piece you need is you need to add this proxy formula, and I'll explain more about why you need this and what it does. But the idea is that you're going to end up modeling the predictions as a function of other variables in your model, and then by using that model, adjust your misclassification. Anyway, so when we do this, we can get back out. So now the annotation sample has 10,000 of the annotations. And the error correction has those 10,000 annotations, plus all of the automatically classified data. And so we can see how, in this perspective example, we get back out the error correction method agrees pretty much with the manual annotations, but you can also see that the error bars are larger, right? Reflecting that we're accounting for the uncertainty that's introduced by using the automatic classifier. But we've managed to eliminate the bias. And then it also works in the dependent variable case. Here, again, the error correction methods, like with the manual annotations, weren't able to, or correctly didn't sort of falsely estimate a negative relationship between likes and automatic classifications. Okay. All right, so now I'm going to talk about how does this work. That's sort of the wind up, and yes, we can do it with this R package, kind of advertising that. Now I'm going to get into like the more technical part of the talk, and I'm going to introduce some notation. So Y, our dependent variable, our outcome. X, our independent variable. And then W is the automatic classifications. Sometimes they're going to be for X, sometimes they're going to be for Y, depending on whether we're automatically classifying an independent variable or the outcome. And then, importantly, there are other observable variables, Z, and this is important because in multivariate regression, measurement error in one variable will affect the estimates for another variable in that model. And then I'm going to have some charts where I have this gray circle, and that indicates that that's the variable that we're measuring using the automatic classifier. Okay, on this slide, I'm breaking down the types of scenarios, the types of problems related to measurement error misclassification into 4 types of problems. On the top row, we have cases where we're classifying an independent variable, X. On the bottom, we have cases where we're automatically classifying a variable, Y. These are Bayesian networks. You may have seen like causal DAGs or Bayesian networks before. Bayesian networks are a way of representing the conditional independence structure of your variables. An edge between 2 nodes means that those 2 nodes are correlated, and that correlation cannot be accounted for by any other variable that you can observe. And so for example, on the top, under sort of example A, there's no edge between W and Y. So there might be a correlation between W and Y, but if we can condition on X and Z, we would know that there was no correlation between X and Y after we did that conditioning. Does that make sense? So not everyone may be familiar with conditional independence, but it's important to understanding what kinds of cases this method can work. or different methods that we're going to talk about can work. So anyway, on your left, we have cases where there may be a bias in the model, but the bias is not correlated with the other variables in the analysis in such a way that it creates additional problems for some of the error correction methods. In technical terms, A represents non-differential error. B represents differential error because of the direct relationship between W and Y. Because W and Y are conditionally dependent given the other variables. We have differential error, and this makes it more difficult to correct. Similarly, D, because there's correlation between Y and W and Z, this misclassification is systematic and more difficult to correct for some of the methods. Okay. This is like the most technical thing that I'm going to talk about. But yeah, from here on, interrupt me if you have questions, because if I lose you, you might have a hard time understanding. Okay. Yeah.
So, your framework, which of those four types of misclassification does it seek to correct?
So our goal will be to have a method that works in every case, right? But there's a number of different methods that might work that I'm going to talk about, and some of them work in some of the cases, but not others. But yeah, the goal is to be able to have a method, or at least some combination of methods that would work across any of these types of scenarios, right? Thanks. Anyone else? Okay. I'll continue. Okay, so now I'm going to talk about the method. This is my preferred method, and it's one that I drew from the biostats literature. On the footnote is a textbook called Measurement Error in Nonlinear Models, and that's the place to go if you want to dive into the theory behind this. But sort of at broad strokes, the idea will be to use the manual annotations, the validation data, to model the automatic classifications, and this will require specifying 2 to 3 models. The main model, which is the model that you want to estimate. This is like a model of scientific interest. You have the outcome, Y, given X and Z, and the other variables. And then there's a proxy model, automatic classifications given the other variables. And then you also need a model for the for the annotations X in the case where you're classifying an independent variable. And the overall idea is that we're going to integrate out the missing annotations by jointly fitting a product of these 3 models via maximum likelihood. And then if the main model and the proxy model and the truth model are all valid, then theory promises that we'll get consistent estimates. And because you can put Y into the proxy model, that gives you the opportunity to account for differential error. And as long as you can put, and you can put any variables in the proxy model in the DV case, and then, so in theory, that should also be able to account for systematic error. So in theory, this should work in all the cases. Some prior social science work has proposed other methods, regression calibration via generalized method of moments, multiple imputation, and pseudo likelihood. I'm going to go into a little more depth on these really quick. So this GMM calibration idea, it uses 2-stage least squares with a trick. 2-stage least squares, if you're not familiar with that, it's a commonly used procedure in econometrics, like in an instrumental variables causal estimation strategy. But here they're using it for a different purpose. The idea is first you estimate a model for X, given everything else, and then this lets you estimate X for the whole data set, not just including the validation data. So essentially, you're building another model to predict X using the predictions of the model you're already using to predict X, but because you can add other variables to that model, now you might be able to better account for that model's misclassification. And then in step 2, you estimate the model that you wanted to estimate using the predictions for X instead of X. But then there's a smart step where you can combine the estimates from your validation data and these automatic classifications using a procedure called the generalized method of moments. And this lets you account for the uncertainty in your estimates of X in step 1, and also efficiently use the validation data. And this is great. You don't have to make distributional assumptions, so you don't have to. It doesn't matter if X or Y are normally distributed or what. And you can but the problem is that you can't put Y in the left-hand side in step 1. And so there's not really much hope of addressing differential error in this procedure, and this procedure doesn't really do much. There's really no way of putting of dealing with misclassifications and Y in this procedure. The multiple imputation, the idea is to treat the data where you don't have validation data as missing data. And so as before, we're going to estimate a model for X given everything else. In this case, they're using expectation maximization and Bayesian framework. But the idea is you're going to repeatedly sample data sets that impute these missing values for X. And then you're going to estimate the model of interest again and again for each of these imputed data sets. And then you're going to average each of those estimates and account for the uncertainty in those estimates using a formula called Rubin's rules. And this is good because you can account for differential error because you can put Y in the left-hand side of step 1. It's also, you can also, in theory at least, account for misclassification in Y. And you can also easily work with more than one automatically classified variable. And there's some limitations, though. I think the theoretical foundations for this one are relatively weak. They assume that the data is all multivariate normal, but obviously our variables are categorical in this setup. They might not be multivariate normal. And this is also a pretty complicated procedure, both computationally and conceptually. Okay, and there's one other thing we tested, which is the pseudo likelihood method. The idea here is that instead of actually using validation data, you'll just use summary statistics from that validation data. For example, the negative predictive value and the positive predictive value. So these are like things you would get from the confusion matrix. And then similar to what we're doing with MLA, or the maximum likelihood adjustment that we're introducing, you can use these statistics to weight the likelihood of Y. And the good here is that you don't need validation data. You can just use these confusion matrix statistics. But there's some problems. One problem is that you're not accounting for the uncertainty in your estimates of the negative predictive value and the positive predictive value. Another problem is that there's not even there's like really nothing in this model except for the raw like statistics. And so you can't account for differential error or systematic misclassification. And then also in this paper that I'm citing, it was an archive and it's missing now. I don't know what happened to it, but there might have been a mistake in the derivation. So I think this is a little bit of a artifact of the process by which we did this paper, that it's still included. Anyway, so I didn't need that slide again. I'm running lower on time, so I'm speeding up. Okay. So as someone asked, we want a method that'll give us consistent estimates, accurate uncertainty quantification, whether or not we're measuring X or Y, and whether misclassification is differential or systematic. And we do some simulation studies to test out each of these methods. So in the IV case, we were going to simulate Y and Z that are normally distributed, and X, which is a Bernoulli variable with it's just a coin flip, probability of 0.5, and it's going to be missing at random. And then we're going to, in that, we are randomly having a sample of validation data. That's our X. And it's going to be correlated with Z. And then our classifier predicts X with about 73% accuracy. So this is below the standard like bar that we would normally expect to see in like published work that uses an automatic classifier for this kind of purpose. But part of the point here is that I think you can do that as long as you can correct for it and account for its errors. And then I'm going to show cases with differential error and non-differential error. In the case with differential error, it's pretty weak. There's just a correlation between X and Y of about negative 0.2. And then we're repeating the simulation 500 times. Okay, and so now I'm going to show some results. So we want to be able to show two things here. One, we want to be able to show that the methods of interest get back the same answer as this feasible, or as it's on the dot. Let's start with on this dashed line. So the dashed line shows the true value, and then basically the bar shows the range of 95% of the estimates over the simulations. And so in this first case, most of these methods actually do a pretty good job, where we have non-differential error with a misclassified independent variable. So the generalized method of moments works, the multiple imputation works, maximum likelihood estimation works. And we can also see that part of how they work is that they get more efficient as we add more automatically classified data, right? So we're not just working with just validation data, right, we're actually getting statistical power from the automatic classifications, even though that automatic classifier is like pretty weak. And so, but then when we add the differential error, then some of these methods start breaking down. In particular, multiple mutation still works, kind of as we expected from the theory, but the generalized method of moments calibration model, it doesn't work as well anymore, as we also kind of expected. But multiple mutation still works, and our maximum likelihood adjustment procedure still works. So in summary, the automatic classifications in this example, they're wrong and confident they get the sign wrong. The pseudo likelihood and GMM methods didn't fix differential error. The multiple mutation method was effective but inefficient. You can kind of see that as you move from like 1,000 to 10,000, and you see how much the error bars shrink, or not the error bars, the range of estimates shrinks. And you can see that for the multiple mutation, it just like doesn't shrink very much compared, and the maximum likelihood adjustment shrinks more. So that's what I mean when I say it's inefficient. And then our method is more efficient. Okay, now I'm going to talk about the DV case. It's like the IV case, except now we're predicting Y with, again, about 73% accuracy, and the errors are correlated with Z. And again, Y is binary, and we have 200, observed 200 times, because I'm showing, sorry, forget about the, okay. Here's the results for the outcome. Then now we're predicting Y. So GMM is missing because it's not designed for that. There's not really even like any way of asking it to. So in the dependent variable case, the pseudo likelihood method, it actually seems to work okay in this case. I think that because I think that the error in its derivation was only in the IV side. And our method is, again, it gains efficiency, and this is with non-systematic classification. But weirdly, and I haven't really found a completely satisfying explanation for this, but the multiple imputation method didn't work in this case where we're automatically classifying the dependent variable. And then, so now when we have systematic misclassification, again, only our method was able to deal with this one. But even it doesn't get that much additional statistical power from the classifier in this case. So if you turn up the accuracy of the classifier, it does a little better. So in sum, the automatic classifications, they were wrong, they were confident. The pseudo likelihood method didn't fix a systematic error. Multiple imputation, it didn't work in the DV case, but the maximum likelihood method, it worked and it was consistent, though there's potentially some room to improve efficiency. So in sum, yes, we can. And I'm going to talk about some limitations in future work. So this all assumes that we have a correct model for W. But in the case of supervised machine learning, I think this is often feasible, because if you're building that model, you know everything that determines that model's predictions. And so you can put all of those things into that error correction model. You don't have to worry about omitted variable bias. You might have to worry about like model specification, like if you have interaction terms, or if you have nonlinearities, or you need the right kind of transformation of the data. But it's not like a deal, there's not like a showstopper like missing variables in that. And then I think it's also an open question about how much we can tune sort of the bias variance trade-off when we build classifiers in order to optimize statistical power for this kind of application. So for those wondering what bias variance trade-off means, you can sort of think of there being a range of modeling options, some of which will prioritize getting the right estimates for parameters, and others of which will, but like getting estimates that are going to be not necessarily the closest to the truth, but that are going to be right on average, right, unbiasedness, right? But those estimates might be very uncertain. And classical statistics usually tries to minimize variance while maintaining unbiasedness. However, machine learning takes the opposite perspective and kind of forgets about unbiasedness, at least when it comes to estimating parameters, and cares about precision and lowering, especially precision of predictions, in order to make the best possible predictions. But if we're trying to use machine learning in order to estimate a parameter in this kind of context, maybe a simpler model where it's easier to model its errors or understand what those errors are, what they could be associated with, would be better than a complex model that has an error profile that's difficult to understand or model. And then I think another important direction for future work is that, so all of these methods assume that the annotations, the validation data is error-free, right? But in practice, humans are subjective interpreters, they make mistakes, and obtaining high-quality annotation data can be a big challenge. And so it could be interesting to explore models that could account for uncertainty from human judgments at the same time they do this kind of error correction step. All right, that's all I have prepared. You can see these are QR codes you can scan to find the package on GitHub or the paper. And I have a bunch of time for questions and also some backup slides if you want to dig into the math. We can do that. Yeah, I'll stop there. Yeah.
Just out of interest, so you were using the toxicity, like the comic toxicity data set?
Yeah, the perspective API, yeah.
Cool. And the classifier you used was like 73% accurate. I'm just wondering, like, is that state of the art?
So this is a very widely used classifier. It's been used in hundreds of papers. I think that the particular, I could get into yes, is it state of the art in that sense that it's what everyone's using? Yes. Could you do better? Possibly. We could also talk about whether toxicity is like the right concept to be measuring or using as like the foundation of how we decide what kinds of posts should be allowed on social media. But yeah, I think that's pretty good. I mean, I think also was an F1 of 0.8, and that's definitely considered good for this kind of task. Yeah. Yeah. Yeah, so the question is about like what are the applications of this project and maybe applications of like toxicity classification or like so taking a step back, maybe I should have like maybe for the audiences I've given this presentation before it would be taken for granted. But so this is basically what's happening is that people want to study a phenomenon like toxicity, right? And they want to be able to measure it, use it in data. That's like unstructured, like these social media posts or tweets or what have you. And so now this perspective API itself is probably more designed for like online community moderators, people running forums or like news websites where they want to be able to screen comments and then find the ones that are predicted to be toxic and then moderate those more, like basically decide whether they should be allowed or not. And I think that this model is totally great for that purpose, right? And a lot of these models are really good for such purposes. The issue is that the engineers that build those models have these purposes in mind, and the standards of like accuracy are often constructed or built with those types of applications in mind, right? Like how accurate does the model need to be in order to be a useful screening tool is a different question than how accurate does the model need to be a statistical measurement device for scientific study. And another question is, my point is that maybe even asking how accurate that model is, if that model is accurate enough, isn't quite the right question. The right question might be like, can we get the right combination of an accurate model and validation data to test our hypotheses, or do some other sort of statistical analysis that we can draw conclusions from. Does that answer your question? Yeah.
I'm not entirely familiar with like computational social science, but I was just kind of thinking, Daniela Witten in the biostatistics department here has kind of like introduced this concept of like double dipping in data,
Mm-hmm.
right? Where like if you run like an unsupervised model to cluster things, then if you go through and then like run some statistical tests to compare the clusters, you've introduced like some data leakage basically. Like that's not like kosher, if you will. that at all? It seems like automated content analysis is like an accepted thing to do in this field, but yeah, I'm always kind of like interested in like hearing.
Yeah. Well, you just want to think about data leakage. The question is yeah. So the question is about data leakage. Sorry for interrupting. Did you finish your question? Okay. So the question is about sort of, is this a method that can deal with the problem of data leakage? And my usual understanding of what data leakage is a concern about is like, say you train a model and then you validate the model on the same training data set, and your model might overfit to that training data set, and so then the statistics that you estimate to try to validate that model might be misleading, or like the precision recall or accuracy metrics, for example. And then there's also concerns that where like that are similar and related, where if the classifier is overfit to the same data that you're doing statistics on, then those statistics may not generalize well to other populations. And I think my answer is that I don't think that like this has anything to do with like really the fundamental issue of like overfitting. I think that the hope is that if you were to train a model in one context using a large data set, and it was really accurate in that context, and you want to apply it in a different context, right? And maybe it's overfit to that context. It's not going to generalize well to your context. But maybe with a smaller sample of validation data in your context, you can still use that model even though it's performing less well, right? And so that's, anyway, does that make sense? Yeah.
No more questions? I thought that I saw a hand earlier. No?
Yeah.
I'm also not like completely familiar with like the computational social sciences, but and you may have already mentioned this, but what about like the ensemble like methods that take like multiple classifiers, and then if something is misclassified, then it feeds into another, and then
Mhm.
it feeds into another, and then it feeds into another.
Yeah, so the question is like, so do ensemble methods like where you maybe have several different types of machine learning models that you fit to your data, and then you somehow average over those models' predictions to make a better prediction. I mean, I think that is like often a useful technique in building machine learning classifiers of various forms, but I don't think it's much of a hedge against the types of misclassification error or bias, right? Like, so it's like that might help you get a more accurate classifier, or maybe even a less biased classifier, but it's not like, it doesn't really matter how, I guess like, it helps to have a more accurate classifier because the room for the types of bias that I'm trying to fix is smaller, right? But it's not, it's like, I guess it's just like a little bit of a different technique. I basically, in this study, I'm basically treating the model as a complete black box, right? It's just like, all it is like a bivariate logistic regression, right? If you actually try to, so on the topic of ensemble models, right, where that would connect is to my question about like the bias variance trade-off, right? So an ensemble model ends up being a really complex model with a large number of parameters, and that would be the kind of like approach that I would be worried about your ability to actually model those misclassifications effectively, or just like figuring out how to model that could be a bigger challenge than if you had a simpler model that might be like a little bit less accurate, but that would at least, yeah, but that would be easier to account for those model the errors. Did I answer your question? Yeah. Okay, cool. Yeah.
Did you say that some of this work was inspired by biostats?
Yeah. So the question is this work inspired by biostats? Definitely. The place I found the idea for this method is, I'm just going to scroll back so you can see the citation again. This one. So Carroll et al. Measurement error nonlinear models. These are biostatisticians, and yeah, all the examples in this textbook are from biostats.
What are they, so for reference, like I'm a biologist.
Uh-huh.
I haven't used biostats. My statistics are very weak as a biologist. So like what do they use these kind of computations for in a biology context? If that's easy.
Yeah, well, I'm not a biologist. So I think that, so one really cool example, it's actually not a totally good example for this, but I think it makes the problem kind of clear. Is so if you want to estimate like the prevalence of a disease, right? You use a test, like a medical test, that you would probably try to give to a lot of different people in a population. Now you might have an expensive test, like a PCR test, that still has errors, right? All these tests have errors, but it might be more accurate than like a rapid antigen test, right? And if you can use a smaller number of expensive tests and a large sample of rapid antigen tests, and especially if, or like cheaper tests, and especially if those errors are not correlated with each other, then you can get back out a better estimate of prevalence. So that's the kind of example they would be thinking about. I think another one was like, I don't know. There's a bunch, and I don't understand very many of them. Like a lot of them are like, we have a medical test and we have later on, or we have like one screening tool, and then we want to be able to estimate like the association between, I mean, backing up, one of the things that was challenging about this project was that very few of those examples in that book actually have validation data, right? In fact, this is what makes this kind of case really easy compared to many other cases where you have to deal with measurement error and statistics. Because in the machine learning, if you can build a machine learning classifier for something, you can, in principle, collect validation data to validate that classifier. And so that means, and because you have validation data, then you can use this type of model, whereas a lot of the other models require you to make pretty strong assumptions about what kinds of errors your model might make or your measurement device might make, and how you might, and like how those might be distributed and so on. Yeah, anyway, really good textbook. Yeah, that's okay.
You might have talked about it, but does this framework then give information about like the contribution of each type of error, like because you're trying to correct for those like point errors we talked about.
Mm-hmm.
Does it tell you like which is contributing most to?
So sorry, I should have. Yeah, this is a good question. So the question is like, does the framework help you understand which type of error you have? I should have incorporated this a little bit into this presentation. So I would argue that like if you were to actually try to use this, you should start by trying to diagnose your like analysis and like figure out which type of error you have, because that'll inform which type of method correction you should do, right? But actually testing though is, not that straightforward. But that's not something that like this model would do for you directly. You might, but you can do stuff like, you want to be able to sort of infer these Bayesian networks in a sense, right? And there are algorithms for this, like the PC algorithm. You can do conditional independence tests. There's a whole bunch of those things you can do. None of them are like really like perfectly compelling, because most of them make assumptions about the nature of these relationships, right? So in my simulations, all those relationships are linear, but if they're nonlinear, then you might have to do some more exploratory data analysis in order to understand that. And a lot of the automatic tests may not work that well, but that would be part of the project, would be to try to like decide, is W correlated with Y or not? Anyway, does that answer your question? Yeah. Yeah, I think it would be good to have a slide on workflow here.
Nathan, I was curious about the data set.
Mm-hmm.
Is that a benchmark data set?
Well, there was a Kaggle competition that used that data set, and it's an open source data set. I don't know about, and so it was definitely a benchmark data set in the context of like the Kaggle competition that Google ran to try to correct. Actually, there was a project to try to like eliminate bias in the perspective API, and it didn't work completely well. I think like the initial examples I found, I think those are mostly driven by a subtle like 0.1 correlation between the identity disclosure variable and the errors.
Because the data set seems big enough to, take advantage of the statistical power in your, but you also talk about these methods and being transferable to other fields. So now I was wondering if you're planning on like next steps to make this more available to researchers in other fields, or if the results are going to vary as a function of the data set size?
So I think that so the perspective API example is really just kind of a proof of point, right? It just shows like this type of problem can happen even in this like widely used model. The data set's already publicly available. The code is available on GitHub. The link is at the end here, and I would love for more people to use this. Wait, sorry, I skipped into my backup slides. So yeah, I would love for more people to use this. I think it could be widely applicable across fields, including not just including computational social science. Like, I mean, I pulled the statistical idea from biostats in the first place, and so it makes sense, to use it there. It makes sense to use it in lots of places where you see people using machine learning to try to measure stuff and then do statistics with what they're measuring. Does that answer your question? Yeah. Cool. I guess we have a few more minutes if there's more questions.
All right.
All right.
Thank you, Nick.
Thanks, everyone.